Hello. We will see in this tutorial how to create an aeroulic network. Here an aspiration system with Mechaflux Pro 3D. Here, we are going to use a layout drawing, which is given to us in this form. We have various sections, and so we will model this part of the system. The first thing to do when starting an aeroulic project, or hydraulics or any kind, is to list the conduits to prepare the work. So, here we have 650 by 300, 470 by 300. Here 1000 by 300, etc. So we have a list of some conduits. We are going to save this list in the library, so we can drag and drop them into our interface. We will start by creating these 3 ducts of rectangular section. Using the equivalent diameter tool, we create the duct of 300 by 1000. So its equivalent diameter is 574. For the calculation of pressure drop, aeroulic or hydraulic, we always use the notion of equivalent diameter. As soon as the pipe section is not circular, for oblong or rectangular pipes, the equivalent diameter is always used. So here for a duct of 300 by 1000, we have an equivalent diameter of 574 millimeters. In the library, we use the duct editor to create a new 574 millimeters duct. We will call it Galvo 100 by 300. And we select from the list of materials the galvanized steel pipe, new galvanized steel pipe, ordinary galvanizing. We select, it offers us a roughness, which we apply to our conduit. The creation of the galvanized duct, with an interior diameter equivalent to 574, corresponding to the 1000 by 300 duct is completed. We click on Save. A message confirms that it has been saved in a library. We classify our library to avoid spending too much time looking for items. We are going to create a subfolder in the ducts, which we name Aeroulic Project. We will store all the pipes for our project there. We're going to store the 574 millimeters duct, which we created, like this. We are going to create the other pipes. So we have a duct of 470 by 300, and another of 650 by 300. So still the equivalent diameter tool. (470 by 300). That gives us 408 millimeters. So a conduit of 408 meters. We keep the last roughness used. We will just modify the name here with a width 470 millimeters. And we record in the library. We are going to move it to the ventilation project. We now create the duct of 650 by 300. We use the equivalent diameter tool. 650 by 300 gives us 474 millimeters of equivalent diameter. We create the new 474 millimeters conduit, corresponding to 650 by 300, and we save it in the library. We place it in the Aeroulic project. We have our 3 basic pipes, so we start the 3D drawing of our system. We are going to see how to create connections. So we have a branched network. We start by building the main branch, and then build the offshoots that are connected. Whatever the direction of the flow, we always start with the main section, the single trunk, near the fan. We create a new network, starting from the conduit corresponding to the main trunk, so 1000 by 300. We select it in our library, and drag it into the interface. This automatically creates a new network. We close the library. And we have a start here with this diameter. So in our example plan, the distance between the departure and the first connection is not mentioned. We estimate it at 1 meter. So we use the just length function. And we apply 1 meter. We have a bifurcation, therefore a separation. We select a separation at 90 degrees. There is a branch that goes straight. We adjust the element that goes straight. To avoid selecting points, when positioning the elements, press the space bar. It shows at the bottom, selection off, and it allows to move the cursor without selecting anything. So there, I select the point. And voila, I put my straight conduit. I click on Validate here. I select the conduit going down. And I will also adjust it. I select its base. And then a point that orients it perpendicular. I press the space key to deactivate automatic selection. And I press OK. Our plan here indicates an exit which is in diameter 355. And we also see that the departure here is not done at 90 degrees but at 45 degrees. So we're going to adjust that fitting, make a reduction, and do that part there. We have a start at 45 degrees here, and a reduction to diameters 355. So to start with, the connection is the other way. And it's at 45 degrees. I select that grid point there which is at 45. I press the space key to deactivate the automatic selection. And I press Validate. So we adjusted our fitting orientation to 45 degrees. This part does not really exist on the plan, but we will leave it for the moment, to increase the ergonomics of the installation. Here we need to insert a reduction. So we use the shrink function. This opens the reduction interface. The output diameter must be 355, it is a sharp shrink. And we extend the conduit, to save us some time. I close. So we have our 45-degree connection followed by our sharp narrowing, which we extended with a duct. Now that we have done our reduction, we are going to reduce this length, which in reality does not exist. We select, adjust the duct length, and we will put 0.1 so as not to have a zero length. With this length the duct will not be visible. So the software suggests setting it larger, 0.3, this prevents the elements from being confused at the same point, and thus avoids making the network unreadable. So here we have our starting point, like we have on our plan. Here on this part there. So we start at 45. We have a small length of about 0.2 meters. And we will continue, after here, we will go down a few meters. We adjust the length. To 1 meter. Okay, I continue after. Starting perpendicular to the main trunk. We can see on our plan that here there is a descent. On the ground floor. We are on the first floor, so we have to go down 3 meters below. So, continue after element, and there I position myself vertically. The grid is set to 1 meter between points. I press the space button when I want to refocus. To avoid selecting any point, and I go down to the third point here. We are 3 meters away. We see that the visible length here is 3 meters. I valid. So we will continue like this. We have the connection above the spiral pipe. So how are we going to model this exactly? In the same way as the previous connection. We create a 90-degree separation. We adjust the branch which will continue straight. We press the space bar to deactivate the selection of points. And we will look for the point which correctly orients our conduit, and we validate. We adjust the other branch of the fitting, I can't see well on the plan. But we can imagine that it is in this direction there. We don't worry about the diameter right now, because we're going to do the reduction. We only adjust the orientation of the connection, and we validate. On our plan, we are here. We made this fitting here which goes up with a spiral hose. We estimate the spiral hose is 100 millimeters. And it's a sharp shrink. Here is our 100 millimeters pipe. So I guess he goes a meter further. And we validate. A little tip, when you have finished adjusting a conduit, you just have to touch the Enter key to validate the position. So this section here does not exist in reality. We left it for ergonomics. But we can now adjust its length to its minimum visible length, which is 0.3. We continue to follow the indications of our plan. And we will model this part there, which starts at 45 degrees, with an estimated diameter of 400 millimeters. So always the same thing, create a fitting separation. Adjust the part that continues straight. Adjust the element. With a slightly longer length of 4 meters. Spacebar to disable point selection and enable hovering. And we select validate. So, here we are going to start at 45 degrees. Adjust the elements. I select the base of the element to align the grid to the base of the element. For the grid points give me interesting alignments. And I select the point here that directs my conduit at 45 degrees. I valid. Same thing earlier, the reduction to 400 millimeters. We choose sudden reduction to 300 millimeters. We do not know exactly all the diameters. This being an example, we have dimensional flexibility. We adjust the length of the conduit to its minimum visible length, which is 0.3. So we could continue, but we will not develop more. We understood how to make connections, and how to adjust the lengths and diameters. We are going to do this part again, which may seem complex. So here we have two conduits that leave. We create a separation like this. We adjust. So a small trick to center the screen on a point of the circuit. We select the element and right-click, contextual menu, recenter on the element. We adjust the element so it goes horizontal. I press the Enter key on the keyboard to validate. I do not wish to continue, and I adjust the second branch. So by selecting this point there, I press the space bar to deactivate the selection of unwanted grid points. Here so that I create my bifurcation. This bifurcation represents the system at this point, with a branch of 470 by 300, and the other of 650 by 300. So I had the conduit of equivalent diameter in my library, here. 650 by 300, that gives 474 millimeters equivalent diameter. So I'm going to shrink to 474 millimeters. with a sharp taper. And click on Insert and Extend with Conduit. It saves a bit of time. Adding the following conduit. We will adjust the orientation later. We also reduce the second branch. We have to reduce to 408 mm, so a sharp narrowing to 408. Insert and extend. Here, I made the bifurcation and the reductions, which represent this part there. We are going to orient all this. We adjust the length to 0.3, which is the visible minimum. And the same thing for the other branch. So now here we are going to continue after. Space bar for the hover. And we adjust our behavior using the points of the grid. Same thing for the other branch. So when we select Continue After, it adds pipes of the same diameter, and it also allows us to automatically insert the elbows. We can reduce this length so that it corresponds better to the drawing. We will put it at the visible minimum, at 0.3. And on the other branch too. We are going to continue by reducing this part there. So here, we're going to go to a 355 diameter, with a cone, followed by an elbow. I do the reduction, shrink, and I stipulate 355. And we determine a 30-degree cone. We insert only the cone, at first. And we will see how easy it is to continue, by selecting, Continue After the cone. So here in our plan, we have a bend directly behind the cone. So in fact we're going to do this part there. And then I validate, so what happened here is that we have selected a point, so automatically the elbow is adjusted to join the point. This is very useful in some cases, but here it is not what we want. We really want a 90-degree elbow without worrying about the end point. We select the elbow. Selecting the elbow activates the orientation button. We click on it, and open the elbow configuration interface. And we set the elbow deflection to 90 degrees. We validate by closing. So we created our elbow. We will adjust the length of the conduit to 2 meters. In our plan, we have here a reduction to 550 by 200. We increase this length to 4 meters. We insert the bifurcation. So now we are going a little faster, because we understand how it works. So here, I'm going to adjust the element. I select its base, I go straight, I validate. Here in my plan, I see it's a reduction, so it's 550 by 200. But I need to know the equivalent diameter. The equivalent diameter of 550 by 200 is 352 millimeters. I will adjust the length to 1 meter, for now. And I want a reduction here, to the equivalent diameter of 352 millimeters. And it's a reduction, abrupt. Insert shrinkage, and no pipe behind. Hey. And here we have a shrinking cone. So I select the shrinking element, and I use the shrink function to insert a cone. With a diameter that we estimate to be 300 millimeters. And we continue with a small conduit behind. So the converging cone is directly related to the abrupt shrinkage. Sharp narrowing and cone are practically confused. This piece there does not really exist, here it is welded. So adjust the length to the minimum visible, 0.3 meters. And I validate OK. Here I was wrong. It's not like that exactly. So I remove the cone. After the shrinkage, I have a piece of pipe, so I do continue after. Because here there is a piece of pipe, length 0.6 or so. And it's only afterwards that I have a reduction. So to the diameter that we estimated here at 300. So shrink. Here we will go to 300 millimeters, with a cone at 30 degrees, and we continue with a conduit. There you go, it looks more like our drawing. Then we go back down, so continue afterwards. And there, I go down one floor, which is estimated to be 3 meters. 1, 2, 3 meters. And I validate. Here we continue with a reduction. Shrink, let's say 300. Insert and continue with conduit. We have gone through the various elements. Now we are just going to add regulation organs. We are going to put valves at each outlet. Here, we insert a valve, create a valve. And we select a butterfly valve, which will allow us to regulate the flow rates. and we're going to close it at 45 degrees. Insert. We do the same here, valve at 45 degrees. Same here. We will thus be able to control the flow rates in each of these ducts, depending on the opening or closing of the valve. This will make an example of regulation. There too we will put a valve, otherwise everything will go through there. So we are not obliged to put valves, we could leave open. But here, to be able to have an interesting example, we need a little head loss. On this small diameter, we did not put a valve. Its head loss will be sufficient to limit the flow. So here we have a simplified, aspirational network. It is necessary to select, here, the suction option, so that the direction of the fluid comes from the ramifications towards the pump, which is at the beginning of the trunk of the network. Another very important thing, we must determine the circulating fluid. So here, the fluid is water. For our aeroulic project, the circulating fluid is air. We choose its temperature, 20 degrees. Use this fluid. So there, we have the possibility of returning to altitude. We will say that we are at 0, default value, and we click on OK. So our network is now supplied with air. We are going to simulate a flow rate, as stipulated on the plan. Of 690 cubic meters per hour, in the main shaft. So I select test rate, change rate, and enter the rate I want to test. Apply and run the test. So the MechAFlux Pro 3D software inserts a generator, which produces the desired flow, and therefore the pressure delta, depending on the network pressure drops. So we see here a vacuum generator producing the flow that has been requested in the branch at the beginning of our network tree. We're going to get a little closer. So in this first zone, here we asked for 690 cubic meters per hour. That's the overall suction, here we have 691. There's still a little precision delta. So you can check the flow in each branch. For example here, by modifying the valve openings, we will modify the distribution of the flows in the branches. We could display the pressures in the different organs by selecting, color the elements. We have the pressure scale in each element. We could do a simulation of particle trajectory to see a little bit how it goes in the system. So we select a number of particles, and click on Test Path. We will accelerate a bit. There we see the particles entering the system. It is the aspiration, and therefore which are rejected at the exit. By selecting each of the elements, we see, if we go to the Results tab, on the debit results, we can see the debits in each branch, which is updated here. We are going to stop the test. We are going to leave the culling of the elements. We can edit the piezometric graphs Here we see the window of the piezometric graphs, which will give us very precise information on each part of the network. So here we are going to go back to the start, in the generator which creates a depression. So the static pressure goes negative. We see this conduit here. Let's just show the pressure gains and losses. Dynamic pressure will not be shown. So here we have the pressure drops, in green. And here we have the gauge pressure. We will continue in section 2. Here the bifurcation which creates a pressure drop, we will just show the pressure drops and a gauge pressure. So here we have the pressure drops changing. And we could go to section number 3 and see how the pressure in the system changes. So, we have at the exit of the system an atmospheric pressure. Here, for the piezometric graph, we could edit PDF reports with views of the network. So we add a view, we give it a name. We can add several views. We can display labels and text, which we set the elements we want to see. We will show only the diameter to the length of the elements. So we could zoom in on a part. We will remove the culling from the pressures and take shots on the different parts for our report. We can create a file with these different views, nomenclatures, piezometric graphs, by generating the PDF report here. So that's it for this tutorial on designing a suction system with Mechaflux Pro 3D.